A drone strike has forced Russia to cut crude oil intake at a major pipeline pumping station operated by Transneft, according to reporting from Reuters on February 24th. The facility sustained damage significant enough to reduce throughput, not by destroying the pipeline itself, but by disrupting the pressure management system that keeps oil moving. This is critical. Pipelines don't simply flow. They are pressure-balanced hydraulic systems. And when that balance breaks, exports feel it almost immediately. Today, we examine the mechanism chain. Infrastructure damage gives pressure instability, gives intake reduction, gives export vulnerability. Pipelines operate on controlled pressure gradients. Key components: booster pumps maintain forward hydraulic force. Intake regulators control how much crude enters the line. Pressure sensors prevent rupture or cavitation. SCADA systems digitally monitor pressure, temperature, and flow. If a pumping station is disabled or partially damaged, downstream pressure drops. Upstream pressure can spike. System stability margins narrow. To avoid catastrophic rupture, operators reduce intake volumes. This is a safety protocol, not a choice. Cutting intake does three things immediately: slows crude movement toward export terminals, forces upstream storage accumulation, compresses export scheduling windows. Pipeline systems are designed for steady-state throughput when intake is reduced. Storage tanks fill. Producers must throttle output. Export terminals face irregular supply cadence. Even if only a single station is affected, the ripple spreads across the network. Russia's westbound export system is interconnected. Major arteries include Druzhba pipeline, Baltic export terminals, Black Sea loading hubs near Black Sea. When pressure stability is compromised in one segment, operators may reroute volumes, reduce overall throughput, prioritize certain export corridors. But rerouting capacity is finite. That's the structural vulnerability. Pumping stations are strategically efficient targets. They are above ground, electrically dependent, mechanically concentrated, hard to fully shield. Destroying buried pipeline steel is difficult. Disrupting a pumping node is not. A single strike can disable electrical substations, pump turbines, control rooms, backup generators, and without pressure, oil does not move. Pipeline systems must maintain minimum pressure to prevent backflow, maximum pressure to prevent rupture. If a station drops offline, adjacent stations must compensate. Mechanical load increases, safety thresholds narrow. Operators often respond conservatively. They reduce intake not because the entire system failed, but because they must preserve structural integrity margins. That is the engineering constraint. Exports depend on synchronization. Tankers are scheduled around arrival windows, storage drawdown, pipeline arrival timing. If throughput slows, terminals may underfill tankers. Loading queues form. Insurance and freight costs shift. Even temporary reductions create market signal volatility, not because production stopped, but because logistics precision was disrupted. Energy infrastructure has become a recurring target in the conflict between Russia and Ukraine. Why? Because infrastructure strikes create economic pressure, export uncertainty, insurance premium increases, political leverage. They do not need to destroy the network. They only need to introduce fragility. Let's consolidate the mechanism. Drone strike damages pumping infrastructure. Pressure balance destabilizes. Operators reduce intake to protect system integrity. Throughput declines. Export scheduling becomes irregular. Market risk perception rises. This is not about a single explosion. It is about how hydraulic engineering translates localized damage into systemic vulnerability. Pipeline networks are designed for efficiency, not for persistent disruption. And in modern conflict, that distinction matters.